thought.
Did you have a question?
No. Apparently I figured it out.
Then I checked my phone, I had
Your desk is really much fun.
I know, I'm sorry. I didn't know you
With an arrow.
so many contacts.
I took a lot of notes on Friday.
Land wagon.
I think I wrote them.
I was like, it's okay, I was like,
I know, I saw
Little
them from back
wagon
here. I was like,
restaurant.
what?
No,
Wagon.
Fates.
It's not my name.
I was talking to Jordan.
me, my face. Why don't you use like a distinguishing, everyone has a favorite thing. Like, yeah, everyone has more something.
Eyebrow on the left side.
You
of
with the
brain.
ear.
But usually the person said it, she usually checks it out.
Yeah, I'm a little confused on what we learned on Friday.
No.
So there's kind of a lot confused.
What?
That's why I have a question about the word.
Me too. Well, because it says use as in sign, but it's a cosine. That's why I got
Is it?
confused.
Yeah, I didn't know
Like the
why.
directions
it
said
said-
use, like, write the equation for the sine graph, but it was a cosine graph.
I didn't see that.
16
Oh.
This is the last class in Cal.
Isn't it supposed to be,
Two classes.
like when we divide the negative out, then that makes 8
So,
positive? Oh, yeah.
so itchy.
Not sure,
Crazy.
but.
Yeah.
I honestly say I'm kind of.
I don't think that works anymore.
I don't know,
I'm
it's
still
like, why
crazy
are they
itchy.
why did they say the thing about the sine function, because it's not a sine
Go to the
function?
doctor.
Drives me insane.
Any
Um,
questions?
B?
Yes.
Number 8, it says graph, or like say the equation of a sine, but I thought it was a cosine graph. I was like, I kind of
It looks like a cosine graph, doesn't it?
It's not.
This is gonna
Oh,
confuse me.
I like it.
it's zero.
This is not gonna confuse you. Now, notice, I do notice, and you should have noticed, and it's worth pointing out, because a couple of you may have overlooked this. The directions say, write the equation for the graph in terms of the sine function. So you're forced to use the sine function whether you want to or not. Now, I agree, when you look at the graph screams cosine function. Yeah, I mean, really. Because you're going up to 6, down to negative 6. Over here at 360, which is your period, you're recycling. And you have a good old-fashioned negative cosine graph, right? You just want to go y equals negative 6 cosine x, done. Right? That's what you want to do. But you can't do that because it has to do with the sine function. Now, if I'm going to label this properly, now, eyes would help here. On this guy, the sine function is the one that starts at the origin and goes up. And the sine function is the one that here that's been, this picture is basically a sine function that rather than starting at the origin, starts at 90 degrees. So what is it? It's a sine function that's been shifted to the right 90 degrees. Now, how are we going to show a shift to the right of 90 degrees? What are we going to do? Sub in what? X minus 90 degrees for x. So wow, this looks like the normal y equals negative 6 cosine graph. It's also a positive 6 sine graph. Positive 6 because the peaks are 6. But it's been shifted to the right 90 degrees. So instead of x, it's going to be x minus 90 degrees. That's going to give us the horizontal shift. The 6 is going to give us the peaks that we need, and the period is corrected 360 degrees. So to write it in terms of the sine function, we have to view it as a horizontal shift. That's the only way to think about it, I think, to think of it as a sine function. Sine function starts at the origin and goes up. So that's the way to imagine that, as a 6 sine x minus 90 degrees. And you will find both of these functions are literally exactly the same. They give you the exact same values. But if the question asks for it in terms of the sine function, they're asking you to jump through that extra hoop, to think of it as a horizontal shift. Just think of it, it's just a sine graph picked up and moved to the right 90 degrees. Stupid, one could argue, but that's what they asked, so good. Good practice. Other questions from Norbert? Olivia?
Yeah.
Number 19? Cotangent 3 theta equals 0. So we need to find, first off, angles, or an angle where the cotangent is 0. Now let's think about what the cotangent is. Cotangent is going to be adjacent over opposite, if that helps us. We'll see how much that helps us. Because when I see a cotangent of 0, I'm thinking, wait a second. How are we going to get that? We're going to have an adjacent side of 0? We can't have a triangle in that case. We're going to have to be a quadrant. So let's go to our unit circle. Over 1 up 0, over 0 up 1, left 1 up 0, over 0 down 1. And of course, I say of course, we know that every point on the unit circle is in the form cosine, comma, sine. So for our 0, 90, 270, or 0, 90, 180, and 270 degree angles, we have those values for cosine and sine. Now, if we need cotangent, let's think about this for a second. Remember, you may not. Tangent is sine over cosine. Well, that would make cotangent cosine over sine, because cotangent is just the flip. So we can start evaluating cosine over sine. Here we get 1 over 0. That's undefined. 1 over 0, that's bad. That's very bad. 1 over 0, so that's not it. Here we get 0 over 1 for our cotangent. That actually works. So 90 degrees is a candidate for our angle. Over here we get negative 1 over 0. That's no good. Can't divide by 0. Here we get 0 over negative 1. That does work. So 270 is our other option. At 90 and at 270, the cotangent, cosine over sine, makes 0. Those are your two angles. But you need 3 batches of those angles because our angle is out of 3 theta. So you're going to have to add 360 to both twice over. Then you're going to have to divide by 3. So it's going to be what, 30 degrees, 90 degrees, 150, 210, 270, and 330. It's not that impressive actually, because if you add 360 and divide by 3, you can just add 120. Let me say that again. If you add 360 and divide by 3, you can just add 120. So that's all I did. Each jump here was plus 120 degrees. I just tried to make it fast. Because I know you guys have done a number of problems like this, so it's like redundant at this point. Once you got the 90 and 270, that was all you needed, right? You're locked in, and you just find the different arrangements. Other questions? No.
Thank God I graduated. I feel so bad for these guys. Cotangent, tangent, all that crap. It's like, no, I look at it and it looks like Korean to me.
I actually like that analogy because
Spanish.
it's a different language.
It is.
If you're head down, can you?
Isn't that funny? A mathematician marries somebody who hates math.
Yeah. Works out actually. So, don't talk about math ever around her, which is good. Talk about it enough during the day, right? I think it works out nicely. Nice professional, personal balance. Marry someone who hates what you do. Right? That's obviously she just dislikes the subject. And she doesn't hold it against me that I like it, she just herself doesn't like it, which I kind of appreciate too, the fact that someone can be that honest. Right?
I like
Right?
math. I
She's like, I really hate math, and she told me that the first time we went out. You told me that you really hated math the first time.
Oh, I
I
freaking
said I
hate it.
appreciate the honesty.
Yeah, no,
Cause how many
I'm
people,
remedial when it comes to math.
when it's like, oh yeah, I did my
idiot.
master's in math, blah, 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 you're like, oh, I hate math.
Yeah, I was very honest. If you're looking for another mathematician, it's not me.
Yeah. Or looking for someone just to humor me, right?
Yeah, I mean, you're
Like,
talking to
oh,
a
I
girl,
used to like math back in the day.
you're talking to the girl that converts fractions into decimals and then reconverts them back into fractions.
Why are you taking an extra step?
Because I looked at fractions and I could not understand them. There was nothing anybody could say to me. I blame it on my teachers.
I would blame other teachers too. And shoot, you worked
But
at
balancing
Pizza
is-
Hut for a time.
I did, yeah, in
Yeah.
college.
But balancing algebra equations, that was.
Yeah, balancing out, or chemistry.
Oh, chemistry, right, right. And that's interesting. Okay. It's a logarithm day. Advanced logarithm problems.
Excuse me.
Let me remind us of what logarithms are first.
Back in like 2
I
years
was
ago.
like, this is so.
Remember that logarithms are just another way to write exponents. It's, and I remember the first time we showed this, and you guys were like, what? Yeah, it's just a different way to write it. It's a different way to express something that you already have a way to express. But the difference in expression can be used to your benefit in certain cases, having the ability to express it in an opposite way. Now, let's also remember, we also have laws of logarithms. Remember, log A plus log B. Think of these as exponents. When do you add exponents? When you multiply the numbers. So add the exponents, multiply the numbers. Subtract the exponents, divide the numbers. Think about that, right? Remember, when do you subtract the exponents? When the exponents are being divided. And the last one that's a little bit weird is when you have like a power, you can always bring the power down in front. One of my math professors that I picked up, he said the only two things that can bring the power down are a revolution and logarithms. Yeah.
What a geek.
Yeah.
What a nerd.
Oh, totally.
Nerd alert.
Oh,
Hey, you know what?
Yeah.
Nerds are going places though, I'll tell you.
I appreciate that. I appreciate that for all the math under the busing we've done today. We get there.
Yeah, shoot me in the face.
Yeah, right. Okay, now here's a new fact about logarithms. This one we haven't discussed, but this one can be thought about. Now, think for a second. When you just see the logarithm, let me just write isolate. If you just see a logarithm like this, you're saying, what power do I have to raise 2 to make 4? Right? That's the question that you're asking. Let me phrase this. What power do I have to raise 2 to make 4? What power do I have to raise 2 to make 4? That's the question. What power do I have to raise 2 to make 4? It's weird, right? Okay.
Joke of the day.
Now, so let's think about this for a second. the result of this is the power that 42 has to be raised to make 5. Right? This is, and rather than asking a question, I'll just make a statement, so it's less too heavy. Let's say the power that 42 has to be raised to make 5. Okay, that's still too heavy, but it'll work.
Ugh.
But what is log 42 of 5? It's what you have to raise 42 to make 5. Now, watch this. Watch this. I'm gonna take 42, and I'm gonna raise it to the power that 42 has to be raised to make 5. Listen to what I just said. It sounds reiterative, and it is. I'm taking 42, and what power am I raising 42 to? I'm raising 42 to the power that 42 needs to be raised to make 5. So what am I going to make? 5. Because I'm raising 42 to exactly the power that 42 has to be raised to in order to make 5.
You will use logarithms so much in the real world. Just
bacteria growth.
come on now.
In complex analysis, it's a really important function, but
Whatever you say, dear.
yeah, you can't model electricity without complex analysis. But anyways, yes, it's logarithms. Yeah, I mean, ultimately, none of you may ever use logarithms after high school, ever. But dang it, it's logical, it's mathematical, and it's something that is, even at the university level, considered to be something that everyone should understand. So, now, here's how the book phrases this, because it sounded really wordy, right? It sounded really like phenomenal, the statement, because it was, what am I raising 42 to? I'm raising 42 to the power that 42 would have to be raised to make 5. Therefore, I make 5, right? Because I'm raising 42 to exactly the power that I needed in order to make 5. Now, the book says it like this. The book says, you're painting a house. This is the analogy they give. You're painting a house, the color that you would have to paint the house to be white. So you're painting the house white, right? What you're doing is you're raising 42 to the power that 42 would have to be raised to make 5. Therefore, you're making 5. You're painting the house, like, you're kind of talking in circles in a way. It's like, well, paint the house the color that you need to paint the house to make the house white. Raise 42 to the number that 42 would have to be raised to make 5. In other words, you're making 5, because you picked the magical power on top. So, what if you had something like this? 3 log 3 of 2. You're raising 3 to the power that 3 would have to be raised to make 2. Therefore, you're making 2. You're raising it to just the right power. You're raising it to the very power that 3 would have to be raised to make 2. Therefore, you make 2. What's the point? It's one more way to simplify a logarithm. So if you ever are in a problem, if you're in a homework problem and you see 5 log 5 and 14, it's 14. Yeah.
What is this like, you said mathematicians like to make shortcuts. How is that shortcut?
I just put 5.
You can add it to your list of like tricks.
Okay.
This is a log trick.
Mathematician, magician.
That's all it is. It's a log trick. Do you ever encounter this very often, like in actual like mathematics? This situation, no, not really. But it's just reminding. It's a log trick. It's a logical trick with logarithms. That's all it is. And the only reason the book has it here is just to get you thinking on the level of, okay, I'm raising to the very power I'd have to raise to make 14. Thus, I make 14. That kind of thought process. It's an exercise. That's all it is. It's an exercise. It's like working the logarithmic muscle in your brain. Now, you want to let's put this into motion, shall we? Yeah, we shall. Divide this. 3 raised to the log base 3 of 4 plus log base 3 of 5. You see that big power up there? Yeah, whoa, that's power. But wait, when logs add, yep. Thank you. Log base 3 of 20, when you add exponents when you multiply numbers. And then you say, well, wait, what power am I raising 3 to? The exact power that you would need to make 20. So you make 20. Like zing, zero in right on the answer.
Silly.
Yeah, it's
Had me
logically.
thinking I was gonna have to sneak people points, and everybody did perfect.
Nice.
You know.
Just bring this along to another one?
You could,
You could?
yeah, there's nothing better. I mean,
You're
because the
welcome.
log
Sorry,
is
I didn't
ultimately
answer
just
your
gonna,
question. You're welcome.
the log is gonna spit you out a number.
You're fine.
So can you take a log of a number? Yeah, you can. Okay, let me give you another example. Let me give you another example to see these logarithmic rules in play. What about this? And we've seen something like this before. Log base 7 of x plus 1 plus log base 7 of x plus 5 equal, or x minus 5, excuse me, equals 1. Now, there's going to be a value for x that makes this true. Maybe there's multiple values for x, but at the very least, there are some values of x that make this true. Let's try to figure out what those values are. Whenever you see logs on one side, you're going to want to smush those together. So, when we add exponents, we multiply the numbers. Log base 7 of x plus 1 times x minus 5. Equals 1. Now, when you only have the log on one side, how do you get rid of the log? By taking advantage of what you know logarithms to be. Another way to write exponents. 7 to the first power is x plus 1 times x minus 5. And now this is an algebra 2 problem. Because you have 7 equals that. You can FOIL that and make x squared minus 5x plus 1x minus 5. And then you can set equal to 0 and simplify. X squared minus 4x minus 12. It's always easiest to factor if you can. Can this be factored? Are there numbers that multiply to be negative 12 and add to be negative 4?
-6,
-6 and positive 2.
+2, I can't do basic addition.
But you knew what you wanted to say. It just came out.
Really bad.
That's all. Yeah, no big deal, but you had it up here. I'm certain you did, because you wouldn't have said the answer if you didn't have it figured out. So x can be 6 and x can be -2. Now, here's an additional level of thought that we haven't had problems like this in a long time where we have this additional level of thought, but let's think about this for a second. You get these two x's, you have to ask yourself the question, do either of these x's make sense? Do both of these x's make sense? Do any of these x's need to be thrown out? Well, if I plug in x equals 6 here, I'm going to get log base 7 of 7 and log base 7 of 1. If I plug in -2, I'm going to get log base 7 of -1 and log base 7 of -6. Now let me think about this for a second. Let me force you to think about this for a second. Seven raised to what power is -1? Think about this for a second. Like if this is your unknown, well, let me use it for A. 7 to what power is -1? If you raise 7 to a positive power, you have some number of 7s multiplied, you get a positive result. If you raise 7 to a negative power, you have 1 over 7 to some power, and you're still going to get a positive result. The point of the matter is, no matter what your power is, if your base is positive, you can never have a negative number here. So here's the thought. If that middle number is positive, the base is positive, then you can never have a negative here. If the base is positive, you can never have a negative as that number that follows the base. Because any positive number raised to any power is either going to give you a big positive number or a little positive number. It's either going to give you 7 times itself a number of times, or 1 over 7 times itself a number of times. Regardless, you can never produce a negative from that. Never. Doesn't matter how many times you multiply 7 by itself, you never make a negative. Because you take 7 times itself any number of times, you're always going to get a positive result, because 7 is positive. Thus, looking at our x's, one of them has to be rejected. The x equals -2 has to be rejected. Because when it plugs back in to the original situation, it puts negatives in the logs. So you can never have negative numbers in your logarithm. One of the purposes of this section was to bring you to the realization that you can never have negatives as your logarithms. Your logarithms will always be positive. If you look at a graph, by the way, of your logarithmic function, this will give you evidence. That was a test question, last test. And when you draw in that graph, it looks like this. That's what the graph looks like. Notice, it's all positive, right? Notice the x value here, only in the x greater than 0 region of the graph, right? Because when you look at the x-axis, here's the positive. I'm on a chalk shortage right now. Here's the positive region of the x-axis, right? Everything to the right. Notice how the graph is completely in that region. Never does the graph go to 0, never does the graph slip to the left of 0. The graph is always to the right of 0. The x's are always positive. The graph reiterates the point of you can never have a negative in a log. If you multiply 3 times itself any number of times, you're never going to produce a negative number. So that number that goes into your log has to be positive. That was another realization that this section was supposed to bring up. Why is that? It's just a fact of logarithms, and it's good to know, and it's good so that if you come up with solutions to a log equation, you know which solutions you can accept and which you can reject. Because you have to reject solutions that produce negative numbers in your logs, and you always have to double check now. Anytime you do a log problem and you solve it out, you always have to double check your answers to make sure that they're okay. So that's going to add an extra step and an extra, often overlooked step to logarithm problems. Keep that in mind. Basically, anytime you see a logarithm problem, be on your toes. Because you know that there are tricks involving the logarithms that you may have to be using. So we'll leave it at that. 59 is the section number. Oh gosh, I told you before there's a reason why we do logarithms. We're almost there to the point where we can actually, there's a punchline. We've been waiting the whole semester to get there. It's got to be coming soon. But for tonight, 59, go 9 through 13, that's going to be your logarithm problems. Graph a parabola in 15. Oh nice, we have a shifted sine function in 16, a non-shifted sine function in 17. Let me also have you do 24. And let's do 25 as well. I'm now curious about when we get to the punchline, because I know you guys have been sitting here all semester. Oh, lesson 82, it's coming. Yeah, like 8 followed by 2, yeah. Yeah, no, we jump around, so we'll get there eventually. It'll probably be like the end of March. months of like crescendo.